Relief and safety valves prevent equipment damage by relieving accidental overpressurization of fluid systems. The main difference between a relief valve and a safety valve is the extent of opening at the set point pressure. A relief valve, as illustrated here, gradually opens as the inlet pressure increases above the set point. A relief valve opens only as necessary to relieve the overpressure condition. A safety valve, as illustrated here, rapidly pops fully open as soon as the pressure setting is reached. A safety valve will stay fully open until the pressure drops below a reset pressure. The reset pressure is lower than the actuating pressure set point. Take a look at the following simplified diagram. If this is our set pressure, then the reset pressure is located here. It is lower than the actuating pressure set point, and the difference between the actuating pressure set point and the reset pressure, or the pressure at which the safety valve resets, is called blowdown. And of course, the overpressure is located here above the set pressure. Blowdown is expressed as a percentage of the actuating pressure set point. This is also the case for the overpressure. We'll see this in detail further ahead. For now, keep in mind, relief valves are typically used for incompressible fluids such as water or oil, and safety valves are typically used for compressible fluids such as steam or other gases. Safety valves can often be distinguished by the presence of an external lever at the top of the valve body, which is used as an operational check. This is illustrated here in this example. You can see here a 3D model of a typical safety valve. Recall, safety valves are pressure relief valves actuated by inlet static pressure, and they are characterized by rapid opening or pop action. Safety valves are primarily used with compressible gases, especially for steam and air services. The safety valve is now viewed on a walk-around. Let's now look into the internals of the valve and its operation. Here you can see all the components of the valve and the 2D cross-section corresponding to it. Starting our way from up to down, you can see that a typical safety valve comprises a cap, a spring adjuster, a spring, a spindle, a bellow, a disc, a seat, a nozzle, and a body. You can see also the presence of an upper blowdown ring and a lower blowdown ring, which we'll cover in details further ahead. Now, the system pressure acts on the disc through the inlet connection or nozzle. The outlet of the valve may have a screwed or flanged connection to a piped discharge system. In some cases, however, like compressed air systems, there may not be an outlet connection, and the fluid, which is air, is vented directly to the atmosphere. The inlet nozzle may be of the full nozzle or semi-nozzle type. In the full nozzle design, the entire inlet tract is formed from one piece. This design is preferred for high pressure and corrosive fluid requirements. The semi-nozzle design involves the use of a seating ring, which is fit into the body. This design has the advantage of easy seat replacement. So, the system pressure acts below the disc. In the normal operating condition, the disc is held against the nozzle seat by spring pressure from the top. The amount of compression on the spring is usually adjustable by means of the spring adjuster. Therefore, the pressure at which the disc lifts off the seat can be altered. When the inlet static pressure rises above the set pressure, the disc begins to lift off its seat and fluid begins to escape. But as the spring begins to compress, it exerts a greater force. This additional pressure, which has to be overcome to achieve discharge at the valve's rated capacity, is called overpressure. Recall, we have seen this in the previous video. Overpressure is so higher than the set pressure. The discs are designed such that the escaping fluid acts on a larger disc area, therefore increasing the applied force which is required to overcome the overpressure. This is achieved by means of a simple shroud arrangement or by upper and lower blowdown rings, which provides a volume called control or huddling chamber. As observed here, once the disc opens, the escaping fluid acts on a larger disc area, therefore providing an additional force. The flow direction is also reversed, therefore providing a reaction force which further enhances the lift. For compressible fluids, an additional factor is the rapid expansion as the fluid volume increases from higher to lower pressure area. Therefore, when the system pressure increases over the set pressure, the disc rapidly pops open, and so discharging the fluid and relieving the excess pressure. Once the normal operating condition is achieved, the valve is expected to close again. But since a large area of the disc is exposed to the fluid, the valve closes only when the pressure drops below the set pressure. This difference between the receding pressure and the set pressure is known as blowdown and is usually expressed as a percentage of the set pressure. The design of the shrouds or the setting of the blowdown rings decides the value of overpressure and blowdown. The upper blowdown ring is usually factory set. The lower blowdown ring is also factory set, but can be altered under certain circumstances. In the top position of the lower blowdown ring, the overpressure decreases and the valve pops rapidly, but the blowdown increases and vice versa.